Welcome back to the next video. In this lecture video, we are back to the ANSYS solver or ANSYS Workbench window. I have imported the flow fluent over here, and in the geometry section, we need to add up the model what we have created in the CAD software, that is the step file. Now, first and foremost thing is to ensure whether the analysis type is set to 3D. And since we are dealing with a three-dimensional flow field, so we have to ensure that the analysis type is selected to 3D. Now we can simply right click over here, go to import geometry, click on browse, and from there we just need to tap on part file or the step file what we have saved in the respected folder. Click on open over here and you can see a tick mark over here. If you really wanted to visualize the model in the workbench, you can just double tap over here and view it in the space claim, or you can just right click and view it in the design modeler as well. Since I'm pretty satisfied with the model what I have created, and I don't think that I need to apply or perform any kind of operations in the model, so I will not be trying to waste the time and opening and waiting for the design modeler or the space claim to open and see whether everything is fine or not. I'll be just heading to the meshing directly, okay, because I'm sure that the model what we have created is appropriate for this particular case. So we will be creating directly the mesh of this particular model, and I will be double clicking on the meshing folder or the meshing module and wait for the mesh module to open. So we are into the meshing module of ANSYS Workbench, and you can see that the 3D model what we have created in the CAD software, that is Creo, it is exactly similar available over here. There are no particular changes in the model, and that really will not happen generally. And you can see that we have this face over here, and the walls, the ceiling wall, the floor is again divided. So just remember that we need to select all of them appropriately when we are naming them. Now you can just visualize the model in different forms as well. If you want to view it in shading with edges, you can have this particular first option, and this is only the shading, no edges, and this is the wireframe. Okay, you can see the internal structure of this particular model as well. So it depends on your interest as to what is suitable for you to represent. Nevertheless, these are all display options which are not quite significant and will not impact the simulation. The impactness will totally depend on the kind of quality of mesh what you are creating. Now, first and foremost thing is, since this is the first time I'm dealing with an academic version 3D case, so I will be directly creating a mesh and see what will be the default mesh configuration which we will be getting, and the number of cells what we will be getting with the default generation. Okay, now you can see that this is a tetrahedron mesh. The elements are in the tetrahedral shapes. Okay, and the sizes are quite large, and this is a very coarse, significantly coarse mesh. Okay, and we will just go to statistics and see what are the number of elements in the domain. The number of elements are mere 8,000. So this is a extremely low number of elements, and the complete elements are quite coarse. So we can try to refine the mesh. We will not be going with structured mesh strategy. The tetrahedron mesh, unstructured mesh will be sufficient for our case as well. It is not really desired to always try to create a structured mesh. It depends on the case. If we are able to solve the case with tetrahedral mesh, there is nothing wrong. Eventually the CFD results stands out. Okay, that is more important. So I really feel that having a knowledge of creating a structured mesh is well and good, but also to achieve a proper result, that is more important, right? End of the day, nobody's judging your mesh. They are basically seeing your results, the novelty in the results, or the kind of comparisons which you're doing with experimental data are attained or no. No one will ask you and force you to select structured mesh or go with unstructured mesh. It's totally dependent on the user, the geometry, and the complexity involved. Eventually, if your results are achievable with unstructured mesh, I feel it is better to go with unstructured mesh, because that will save our time. and to create the structured mesh as well. Now what I will be doing is, firstly I'll see what is the default element size. It is 4 point something, e minus 2. So e minus 2 stands for 10 minus 10 power minus 2. This indicates the general element size is 0.04 meters. Okay, so it is 4e minus 2. I'll just half it. I'll make it as 2e minus 2 and generate mesh. Now the meshing will happen again, and you can see a reduction in the size and increment in the number of elements. So this is again 76,000, which is pretty lower than the limit what we have in academic versions. So I can again halve it, 1e minus 2, press enter, and see what will be the number of elements being generated in the complete domain. All right, and there it is, 47% completed. So the refiner the mesh, or the lower the element size, the larger time it requires to create the mesh. And now you can see my the fan in the computer is being turned on automatically, and the number of elements are pretty high, that is 378,000. So if you want, you can just try to reduce them as well if you're really wanting them to be reduced. Then this is the first simulation, we can go with a little 1.5 is sufficient, minus 2. As I always say, you have to go for three kinds of element sizes, coarse, medium and fine. Like you can go with 2e minus 2, then 1.5 e minus 2, and then you can go with 1e minus 2 and see the differences in the results. Okay, the result like x velocity, what they have mentioned in their paper, that can be compared for three meshes, and we can understand what level of mesh is giving us appropriate results. So if medium mesh is giving us the exact results, so we can stick for the same mesh size for the next consequent simulations, whatever we are doing it. Okay, so this is an unstructured mesh. You can just try to visualize the cross section of this as well if you're really interested to do that. And for that, I think we have to go to display option over there, and we have to, let me just select geometry over here, go to geometry, home. Yeah, in home we will be having this option. So you either be in geometry mode or mesh mode. You just go to home, you have something called as section plane. Okay, so the options of visualizations of sections and all are little complicated in ANSYS in comparison with designated designing software such as Creo. Okay, you might have remembered in the previous video I've easily created a section view, but here we just have to click on this. You'll be having one window opened over here. You just need to click on new cross section or new section, and after that, what we have to do, yeah, so for example, just align the view to normal view. If I want to create a section over here, after clicking on new, now the cursor, you can see it is a normal rotate mode. Okay, now I'll just click on new over here. This is activated and my cursor is in different mode right now, so I can create a cut section over here. So I can just utilize my left click over here, create a cross section and leave it. You can see automatically it is being created. So this is how your model is inside. You can see the mesh being created over here inside different size, and this is a cut section model, cut section shape, you can say, right? So what you can do is, I believe you can try to how do you do it? Yeah, you can select this section what we have created, turn off and turn on, then click on edit section. You'll be having this bar like feature, and select this side or this side. Okay, the other side will be captured, and if you want to just move, you can just drag it over here. Okay, and you can understand how the mesh is being created over here, right? So this is the final wall. We are just moving inside and outside. I'll just delete the cross section. I just wanted to show you. So that is it, what we have done. Now I'll stop the video over here. In the next video, we will be renaming all the desired sections. Now one more thing what you can do is, if you want, you can see the inlet over here. It is having a very low number of elements over here, so you can just refine the mesh in this position, in this region. So you can just select the respected face, go to mesh, and go to sizing over here. So now you can see face sizing is being activated, and here also the default size is visible over here, right? Now what you can do is, for this specific single face, you can increase the number of elements by reducing the default size. The default size of the overall model is 1.5 e minus 2, and for this one I'll just make it as 1 e minus 2 and see what is going to happen. Click on generate, and it loads for a while. You can see the meshing is being created, and there is my slight refinement that has happened over here. Okay, now the mesh is completely unstructured, remember that thing at this moment as of now. And if you really want more number of elements, we can do this thing. So I'll just make it as 0.005. Click generate over here, and you can see overall the number of elements are increasing, and you can see a kind of refinement over here. That is the reason the mesh is quite dense in this region, right? You can make it further below if you're interested. So it depends on your this is how much, 0.002, that is 2e minus 2. It depends on your limitations of your license. You can go to that level. Okay, so generally wherever you have an area of interest, for example the inlet, the outlet, or if you have any significant feature in the domain, like for example any occupants, right? The region of space closer to them may be refined a bit more in comparison to the global spaces, okay, that is far away from the region of interest. And for refining, we can just use face sizing option, select the respected phases, and just uh, enter the element size and see the significant changes that are happening in the mesh. Now I really believe that this value what I have used over here is quite low. That is the reason it is taking much time for completion of this meshing. Nevertheless, let us just see what is going to happen. If not, we can just try to increase a bit and see whether we are able to achieve. Now the reason for this offer to take a lot of time is because you're not just dividing the complete inlet. The associated or nearer elements also gets disturbed, so they are also adjusted by the software automatically. So that is the goodness of unstructured mesh, that it adjusts automatically. And but yeah, you have to always check the validity of the mesh, that is with the help of grid independent study. You cannot directly say that unstructured mesh is good. And no matter if you're going with unstructured mesh or structured mesh, the validity of the mesh has to be checked with the help of grid independent study. So that has to be performed. Then if possible, comparison with the of the domain of the results with experimental study must also be performed. So these two factors can contribute to prove the authenticity of the mesh or the grid what you're using in your case, name it unstructured mesh or name it as structured mesh. Clear? Now I really feel this is taking a lot of time, and we can just wait for a while and see whether this will complete or no, and let us see whether it is able to achieve the desired result or no. So I've just clicked on stop because it is taking a really lot of time. So I'll just keep it as 0.005. Click on generate the default previous value. Okay, I'm sorry. Yeah, so let us just wait for this. Yeah, so finally this is completed, and what we can do at this moment is we can add the same face sizing to the outlet as well. Okay, and the final size was 5e minus 3 for this face. So I'll just click on the mesh, pan the geometry, zoom over here, select this face, go to sizing and enter the same value, that is 5e minus 3. Press ok and click generate, and wait for the solver to complete the meshing part, and you can see it has refined at the outlet as well. So you can see the inlet region and the outlet region are quite denser, whereas the global region is quite medium. Okay, now the next task in the next video, we will be adding the wall boundaries or the names or naming them, and then we will import them into the, or we will push them into the physics setup. So let us just move to the next video.